This video is about phases and the phase changes they undergo. You should already be able to identify gases, liquids, and solids and explain their properties based on intermolecular forces of attraction and use and explain points on a phase diagram, but we're going to review that and explain specific properties of liquids such as viscosity, heat of formation, and subsurface tension in terms of intermolecular forces of attraction. So this is a review of IMFs. The question of the video is, why can Jesus lizards walk on water? And it has to do with the intermolecular forces of the water. So the properties of liquids that we need to know is first surface tension. It's elastic force on the surface of a liquid, and the higher the force, the stronger the surface tension. So if you look at the little diagram, the particles in the middle are pulled in every direction equally and therefore stay somewhat stagnant. But the ones on the top are being pulled down only sides and down. There's nothing being pulled up. In that case, the whole top is being pulled down like gravity, and it creates a tight surface for a limited amount of time, just tight enough to as tight as its intermolecular forces are strong. And so that would explain why in the previous picture, as long as the lizard doesn't stay in one place, it's taking upon the fact that the intermolecular forces are strong enough for those few seconds that it's walking on the water to not actually break the surface. And the water has those really strong hydrogen bonds, which would be why it has such a strong surface tension. Another property of liquids we need to know is viscosity, or the measures of the liquid's resistance to flow. The greater its intermolecular force, the greater its viscosity, and the slower it flows. So if you increase the temperature, the viscosity will decrease because you'll break some of those forces. If you look at the picture, things like syrup might have really strong forces. Water, we said, had strong forces, but maybe not as strong as the syrup. Maybe the syrup is made of hydrogen bonds as well, and maybe many more locations of those hydrogen bonds. Similarly, sometimes it's really hard to get ketchup out of the bottle. That's because ketchup is really viscous. So we should know how to use that term in sentences and descriptions of our observations. And heats. The heat of vaporization is the heat that you need to change from a gas to a liquid, or the heat that escapes when a liquid goes back to a gas. Similarly, the heat of fusion is from solid to liquid, or the heat that escapes from a liquid to a solid. And last, the heat of sublimation is any time you put heat in to go from a solid to a gas without seeing the liquid phase, and therefore it could also be the heat that's released going from a gas to a solid. If the intermolecular force is really strong, the heats of these are all really high. They resist changes in phase because they want to stay the way they are. So in the picture on the right, we're seeing heating curves. These are from last year, but we're going to review them. On the first part of the heating curve, starting at the 0 mark, you have a cold solid. The particles only vibrate within the solid, and they're in a geometric or crystalline solid. Eventually, they get warm enough that they hit their heat of fusion, their temperature in which they melt. And that temperature stays the same temperature. So when they say melting point, it's really the point on the y-axis that they're talking about. It's actually a plateau, a melting plateau, if you want to think of it that way, right? The temperature remains constant as it changes its phase. And we're going to get into the types of energies that are required to change temperature versus change phase. And that's why you're not seeing a change in temperature, because we're changing phase. They're two different energies and they switch on and off. In the next section, we have a liquid phase, which are able to move past each other with no definite shape, but a definite volume that we can measure. And eventually they get warm enough to hit their boiling point. When they hit their boiling point, the particles start to move further apart and become a gas, and the temperature remains the same. Again, this is called a boiling point because it's a point on the y-axis. It's actually a boiling plateau on this graph. Eventually you get a gas, and the gas can get hotter and hotter and hotter and further apart. So if we talk about these phase change diagrams in terms of energy, as we mentioned, and I'm just showing you a water-specific example, whereas the previous example is for pretty much any object that has all three phases. The phase change diagram would have, again, the solid on the bottom, the gas on the top, and the liquid area in the middle. What we want to look at is when temperature is increasing on those spots. The kinetic energy is increasing because the temperature is increasing. So the ice pot is going from -2 to 0. That's increasing kinetic energy. So is on the blue area here, from 0 to 100 is increasing temperature, therefore increasing kinetic energy. The particles are moving faster. And last, on the red area, from 100 to 140, and so on, the particles are moving faster because they have more energy. When the temperature is stable, that's when potential energy comes in. So the potential energy increases along the stable 0 line in order for it to change phase. So whenever it's changing temperature, it's changing its kinetic energy. But whenever it's changing phase, it's changing its potential energy. And they're kind of clicking off. And I tried to color code it so it'd be easier for you to read. So let's look at one more variation, a cooling curve. It's no different. The gas is still at the hottest part of the graph. The cold part is still the solid, and in between is still liquid. We're going to say the gas is getting closer together and eventually condenses. We might call it condensation point, but for some reason only really meteorologists say that. We still call it the boiling point because it would have been boiling in the opposite direction. And then the liquid gets closer together as it cools and eventually freezes. Again, phase changes are potential energy changes, and the particles are getting closer together to become a solid, and eventually the solid particles decrease their speed. So remember, the phase changes occur in the plateaus. So this is condensation, and this is a freezing point, also known as melting point if you went backwards. The kinetic energy changes whenever the temperature is changing. So if the temperature is decreasing along these certain lines, then that means its kinetic energy is decreasing. And then the potential energy changes when you have changes of phase. So if you're going from a gas that has a lot of energy to a liquid that has less, its potential energy is decreasing. Similarly, if the liquid has more energy than a solid, as you go from a liquid to a solid, its potential energy is decreasing. One more question, are the bonds or the forces changing? Again, anytime you have a phase change, all you're doing is getting the particles closer together or farther apart. So when you're getting them closer together, you're creating new forces, right? So we're creating more and more forces, gases having very low forces and solids having many more. On the previous example, we were breaking the forces, making them spread out. This is not to do with bonds. Bonds would require a reaction. So at this point, you should be able to explain specific properties of liquids such as viscosities, heats, and surface tension in terms of intermolecular forces of attraction, and then also use and explain points on the, not triple point diagram, sorry, the phase change diagram.